Today, we're diving into the world of digital security, but with a really cool twist. We're going to look at a clever new way researchers are hunting down those hidden, nasty bugs in the software we use every single day. So, you've probably wondered this, right? You get the latest, shiniest new app, you update your phone, and then a week later, you hear about some major security flaw. Why does this keep happening? Well, the honest answer is, it's just incredibly hard to find them. Modern software has millions of lines of code. It's this enormous, sprawling digital landscape. And finding one tiny, dangerous bug in all of that is a monumental task. And we're not just talking about a minor glitch here and there. These hidden bugs are a huge, ongoing problem for pretty much the entire tech world. Think about it. Our whole society runs on software now. Our banking, our communication, even critical stuff like the power grid. So making sure that software is secure before it gets to us, it's one of the biggest and most important challenges in technology, period. So how do the experts actually hunt for these things? Well, one of their most powerful tools acts kind of like a digital detective. It's a technique called fuzzing. So what is fuzzing? At its heart, it's basically the art of throwing chaos at a program, but in a controlled way. You have an automated tool, a fuzzer, that just bombards the software with millions of weird, random, and broken data. The goal? To make it crash. Because when it crashes, that often points a giant flashing arrow right at a hidden bug. And for a long time, the absolute gold standard in the fuzzing world has been a specific method called edge coverage. It's the go-to technique that pretty much everyone in security relies on. To really get how this works, let's use an analogy. Imagine the software's code is like a giant city map. Edge coverage is kind of like a special GPS that gives you a little reward every single time you drive down a new street you've never been on before. So here's the play-by-play. The fuzzer chucks some random data at the program. It watches the path the code takes, and then it asks one simple question. Did we go down a new street? Did we hit a new edge, a connection between two parts of the code we haven't seen? If the answer is yes, the fuzzer goes, ooh, that input was interesting. It saves it, messes with it a little, and then uses that to try and find even more new streets. And it does this over and over, millions, even billions of times. But here's the catch. This digital detective, as good as it is, has a massive blind spot. And hey, don't just take my word for it. The researchers behind this work say it flat out. For a lot of today's complex software, just checking off which paths you visited isn't going to cut it for finding the really tricky bugs. Let's go back to our city map. Edge coverage is great at telling you that you've been on Main Street and Oak Avenue and Pine Boulevard. What it has no idea about is the order you visited them in. It's completely missing the context of the actual journey. And this is the whole problem right here. A really nasty bug might only show up if the program does thing A, then thing B, and then thing C in that exact sequence. But our standard fuzzer, it just sees that A, B, and C got hit eventually. It's totally blind to the importance of that sequence. It literally can't see these kinds of bugs. So this led to a really cool new idea. What if, instead of following the path of the code, we started following the trail of the data itself? The key here is something called a Data Dependency Graph, or DDG. It sounds technical, but the idea is actually pretty straightforward. It's like a super detailed map that follows a single piece of data from the exact moment it's born inside the program and then tracks every single place it gets touched or used later on. It's a totally different way of looking at what a program is actually doing. And this whole idea gave birth to a new tool called DDFuzz. It still does the old-school edge coverage thing to explore, but it adds this data flow map as a second, really powerful clue to help guide its search for bugs. And this, right here, is the perfect way to think about it. The old way, edge coverage, is just a roadmap. It only cares about the streets you visit. But DDFuzz, it's like a recipe. It cares about how all the ingredients, the data, are mixed and combined to create the final dish. It's tracking a completely different and sometimes a much more important story. Okay, so the recipe idea sounds great, but does it actually find more bugs in the real world? Let's take a look at the scorecard. The results are pretty awesome. Across 38 different real-world programs, and we're talking about heavy-duty stuff like code compilers and critical software libraries, DDFuzz sniffed out 72 different vulnerabilities. So, yep, this thing works. Now let's zoom in on one case. In this one library, DDFuzz found 30 bugs, and the standard method found 28. At first glance, you might think, okay, that's a tiny improvement. But hold on, because the real story is way more interesting than that. Get a load of this breakdown. It turns out DDFuzz found 17 unique bugs that the old method completely missed. And the old method found 15 that DDFuzz missed. This is the key insight. DDFuzz isn't just finding more bugs, it's finding a totally different class of bugs because it's following different clues. They're like two different detectives who are good at solving different kinds of cases. What's really cool is the researchers even built a practical tool from this. It's a metric they call the DD ratio. It basically gives a program a score based on how complicated its data flows are. And if that score is high, it's a huge flashing sign telling developers, hey, you should probably use DDFuzz on this one. It tells them exactly when to bring in the specialist. So, at the end of the day, what's the big takeaway here? DDFuzz is this powerful new specialist for finding bugs in really complex software. It finds whole categories of vulnerabilities that our old tools were blind to. And maybe the best part, it does all this without slowing things down too much, which means it's a practical tool that developers can actually use. You know, this is just such a fascinating shift in perspective. Just by changing what we told the computer to look for, from the code's path to the data's journey, we unlocked a whole new way of finding bugs. It really makes you wonder, what other invisible clues are just sitting there in our software, waiting for us to invent the right kind of detective to find them?